In this video, we're going to go over what differentiable really means and why differentiable functions can't have any sharp corners or cusps. Let's jump in. To start off, let's ask the most basic question, what does differentiable mean? So go ahead, pause the video, and see if you can answer that. Differentiable really just means that you can differentiate the function, and differentiate just means take the derivative. So a function is differentiable at a certain x value if it makes sense to take the derivative there. Or another way you could word it is if the derivative exists at that x value. So that's what differentiable means. It means that the derivative exists, basically. So that's what differentiable means. Now let's look at how you can tell whether a function is differentiable or not just by looking at it. First, let's start off by saying that if a function is not continuous, it's not differentiable. So right here, this is a step function, for example. You can see that we have a jump discontinuity here. So it's not even continuous. If a function is not continuous at a certain value, it's definitely not differentiable. It has to be continuous to even be able to ask whether or not it's differentiable, if that makes sense. Differentiability is a stronger requirement than just being continuous. Now here, just to be clear, this function is continuous and differentiable everywhere besides x equals 1. So we would say that this function is differentiable on the interval from, say, -8 to -4, from x equals -8 to -4, because it's differentiable at all those values. The derivative exists. If you zoom in really close, it makes sense to say that it has a slope there. But at x equals 1, it definitely does not. So x equals 1 is actually the only problem point, but in general, we would say this function is not continuous over the real numbers or over the interval from -infinity to infinity. So this is not continuous and not differentiable. This next one is continuous. I can draw this function, the absolute value function, without picking up my pencil. However, it's not differentiable. Why is it not differentiable? Because we have a sharp corner here. Now, again, it is differentiable at every spot except for the sharp corner. It's just not differentiable at the sharp corner. So we can't have that. That's what a sharp corner looks like. Here's a function that has a cusp. It kind of looks like a sharp corner, but it's more like it's bending down. It almost looks like it's approaching a vertical asymptote or an infinite slope as we get closer to a certain value, rather than like a sharp corner. But this is also a problem. So again, this function is continuous. I could draw this function without picking up my pencil, so that still works. But it is not differentiable at x equals 2. It is differentiable everywhere else. So this is another function that's continuous but not differentiable. And then finally, let's look at one that's continuous and differentiable everywhere. This would be like a normal polynomial. So you can see it's nice and smooth and it curves everywhere. There are no sharp changes in the slope anywhere. There are no instant changes in the slope. That's another way of thinking about differentiability, by the way. Smooth is another word that they sometimes use in Calculus 3. But basically, if they say you have a smooth curve, this is what they mean. It's like you don't have any sharp cusps or corners, anything like that. So basically, what we can say is that a function is differentiable at any x value if the function is continuous there and it does not have a sharp corner or cusp. But the question is, why is that? Why can't we have a sharp corner or cusp? In order to understand that, we have to dive a little bit deeper into what the derivative really means. Remember, the derivative is the slope of the tangent line to a curve at any point, and that derivative is fundamentally represented by this limit. In other words, every time you see a derivative, it is this limit under the hood, even if you don't work with this limit directly. Now, I won't dive into the details behind why this limit definition of the derivative makes sense. I've actually already covered that in another video. Instead, I just want to point out at this point that it is a limit. That's all I want to emphasize here. So when we say that a function is differentiable at a certain point, really what we're saying, remember from before, one way to say it is that the derivative exists, and think about that language. The reason we're saying the derivative exists is because the derivative actually is literally a limit. And we can talk about whether limits exist or not. So in other words, a function being differentiable means that this limit has to exist. And what does it mean for a limit to exist? Remember, there's actually a three-part definition. Basically, the left-sided limit has to exist. That's what this means. The limit as we approach a certain value from the left has to exist. In other words, as the x values get closer and closer to a from the left, the y values clearly are getting closer to a certain value. That's the left-sided limit. The right-sided limit also has to exist, and they have to be the same. In other words, if we have a function here, whatever we approach from the left, we also have to be approaching from the right in order for that limit to exist. If we're approaching a separate number, then the left-sided limit would exist, the right-sided limit would exist. They're clearly getting closer to a certain number. The problem is those are different numbers, so we would have a jump discontinuity basically. The limit in that case would not exist. So that's what it means for a limit to exist. And I guess what I'm saying is that you can apply this, specifically the third one, if we assume that both of these exist, to the idea of a derivative. So in order for the derivative to exist, which again is also a limit, this specific limit has to equal this specific limit. In other words, the left-sided derivative has to equal the right-sided derivative. But what does that mean? The left-sided derivative is basically what the slope approaches as you come in from the left to a certain point. So if I'm trying to find the derivative at 0, or the left-sided derivative as x approaches 0, I need to approach it from the left. And hopefully you can see that the slopes are just leveling off, leveling off, leveling off, and it seems like we're getting closer to 0. Now, on the other hand, if I come in from the right, that's what the right-sided derivative represents. It's the slope of the tangent line as we come in from the right. So hopefully you can see that they're starting off very positive, but getting lower and lower and lower. And yeah, it actually also seems like we're leveling off to 0 as we come in from the right. So in this case, for y equals x squared, we can see that the slope actually approaches left as we come in from the right and from the left. Therefore, the left-sided and the right-sided derivative are both x equals 0, are both 0, which means that the derivative itself exists and is equal to 0. That's why the derivative of x squared equals 0 at x equals 0. But what happens if we do the same thing with a function that has a sharp corner at x equals 0? Well, basically, as we come in from the right, you can see with this function, actually the slope always stays -1 here. It's kind of hard to see for that reason. It doesn't change, but the slope is -1 as we come in from the left. And if we reposition on the right, you can see that the slope just stays +1 as we come in from the right. And they don't get closer to each other. That's kind of the point. So they're just staying at -1 and 1. They never level off and get closer to each other like we did before. So basically what that means is that they'll never equal each other. So the left-sided and the right-sided derivative do not equal each other in this case. Therefore, the derivative, as a limit, does not exist. That's why functions are not differentiable if we have a sharp corner. And you can see that a very similar thing happens when you're dealing with a cusp. So again, as I approach 0 from the left, you can see that the slopes are starting off at somewhat negative, but they're getting more and more negative. They're getting really, really negative. So here you can see that they actually seem to be approaching -infinity as a slope, just an extremely steep negative slope. Whereas if we come in from the right here, the slopes are starting off at not very positive, so slightly positive, and then they're getting more and more positive actually as we approach 0 from the right. And they actually start to approach a slope of +infinity. So as we come in from the left-sided derivative is -infinity, and the right-sided derivative is +infinity. Therefore, the left-sided derivative and the right-sided derivative are different, which means that the derivative does not exist there. So it's not differentiable at the cusp. So why does this exact definition matter for differentiability? To understand that, let's turn all of these in and start zooming in around 0. Remember, y equals x squared, the red function, is differentiable here, whereas the sharp corner, the absolute value of x, and the cusp, x to the 2/5 power, are not differentiable. So let's see what things look like as we zoom in. If we zoom in here, you can see that no matter how far I zoom in, the closer I get to 0, because the left-sided derivative for x squared and the right-sided derivative for x squared both approach 0 as we come in from the left and right, the derivative exists, which means it's basically going to start leveling off as we go in from the left and the right. So as we zoom in really close, you can see that, yeah, actually y equals x squared starts looking like a straight line with a slope of 0. However, that does not happen with a sharp corner. So no matter how far we zoom in with a sharp corner, this function will not level off because, again, the left-sided limit, the left-sided derivative and the right-sided derivative do not approach the same thing. They approach different things. So there's always going to be a sharp corner no matter how far we zoom in. And then for the cusp, there's a similar situation. It doesn't look like it can be a straight line. It's basically going to be a vertical line if we zoom in, or it's going to approach a vertical line. So again, it's still not leveling off to a slope that we can actually deal with, which is a problem. So there you go. That is why this function, y equals x squared, is differentiable, because if we zoom in far enough, it will start looking like a straight line with a slope that we can actually deal with, whereas the other ones, y equals the absolute value of x and y equals x to the 2/5 will not. And this is true of any function that's differentiable, by the way. If the function is differentiable at a certain point, you can always zoom in far enough to force that to happen. Whereas when you're dealing with differentiable functions that are not differentiable, I should say, you will never be able to zoom in far enough to make that happen. And that is the key difference. So there you go. Hopefully differentiability makes a lot more sense now. If you have any questions, be sure to leave them in the comment section. Otherwise, I'll catch you next time. See ya.